Hello there. Hope your fall break went well. I'm just going to post a quick video on the remainder of the problems that we did not look at last week. So there's 8 or 9 problems right here, and we're just going to go through them and, find the ones that maybe you have questions on, kind of skim through. If you know what to do with it, you don't need to listen to me talk about anything, but this can be a reference for you. All right. So we are looking at this problem that we left off on. A researcher randomly selected 30 people to participate in a study to investigate which of two materials, A or B, used in the heels of sneakers will last longer. The researcher is considering 2 types of designs for the study. So design 1 is randomly assign 15 participants to wear sneakers with material A on their left feet, material B on their right. The remaining participants will wear sneakers with material B on their left and material A on their right. Design 2, randomly assign 15 participants to wear sneakers with material A on both feet, and the remaining participants to wear sneakers with material B on both feet. Which of the following best describes each design? So we've got design 1 and design 2 being compared. And so it looks like we're talking about they are a completely randomized design, a matched pair design, and then they also throw out the option of blocking. There's no blocking here. Remember, that's similar to stratifying, and we're not stratifying based on anything here. So that would be like if we had men versus women blocked based on their different weights potentially, or we just blocked based on weight, to see if that had an effect. But anyways, we're doing, so remember what matched pairs is whenever you have 2 participants in the survey or in the study, in the experiment, that are similar, and you're going to assign randomly between those 2. You match them up into pairs, the 2 very similar ones. Now, and you randomly assign. So in this case, one person actually has 2 participants. It's weird because it's each foot is a participant in this survey. So when you have material A on the left, material B on the right, or vice versa, you're doing a matched pair design, because obviously your 2 feet are going to be very similar, except in strange situations. So your 2 feet are going to be very similar, and so assigning them randomly between the 2 is going to be matched pairs. So design 1 is matched pairs. So we got these 2 can be thrown out. Now, design 2 is not a matched pair. That is going to be completely randomized, where anyways, you just pick 15 participants to wear A on both, and then another 15 to wear B on both. So the answer here is B. Okay. These types of questions really throw people off with this is not a 2A table, but it's a question on probability. Students at a certain high school have an elective period where each student chooses an elective from among 4 options. The following table shows the number of students who selected each elective for the 1,500 students at the high school. Okay, 1 student will be selected at random. What's the probability that the selected student chose the art elective and the music elective? Okay, now here's what we need to do is, first of all, figure out, are these mutually exclusive or not? So I'm going to figure out, there's 1,500 students, and if these 4 options all add up to 1,500, that means that every student chose only 1 elective. And that seems to be the case from the prompt. So we're going to go through and add it all up. So if I add this up, then we will find that this does add up to 1,500. And so the probability that someone selected art and music is going to be 0, because you can't select both. You have to select one or the other. So your answer here is going to be A. All right, this problem right here, we are looking at a probability distribution. It's a cumulative probability distribution for a discrete random variable X, and it happens to be number of movie screenings at movie theaters in a certain city. And Andromeda, excuse me, Andromeda claim that's a neat name. Claims that the distribution of X is skewed to the right with a mean equal to 4 movies, is Andromeda's claim supported by the table. So remember, the first thing we want to do with something like this is figure out what the probability distribution is. So the probability of X. Now the probability that X is less than, that a random variable is less than or equal to X, but just the probability of getting that specific outcome. So in this, we want to figure out what's added each time. So for 1, we added, it started at, of course, 0. So up to 1, we added 0.2. And then the change from here to here was 0.3. You can do that math real quick. The change for all the rest of these, I believe, is 0.1. So if I go up, like for the next one, 0.7 to 0.8 means I added 0.1 to it, 0.8 to 0.9, and so on. So, if I actually drew out this distribution, this probability distribution, so there's 0.1, 0.2, 0.3. It's going to start out something like this, and then like this. So however many, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's the probability distribution. Of course, it's going to be 1, 2, 3, 4, 5, 6, and 7. You don't have to draw this out. I'm just really making it clear for you. Okay, so the distribution is skewed to the right. Yes, it is definitely skewed to the right. So we can say it's skewed to the right. So I'm going to cross out anything that doesn't go with that. Okay, but the question is the mean equal to 4 movies? Now we can plug this into the calculator and figure it out. We want to figure out maybe where the mean, or where 4 is. Okay, so let's go to 4. Is the mean equal to 4 movies? So I'm going to find 4. There's different ways you could do this. And, the most thorough way is to actually just create 2 lists in your calculator with 1, 2, 3, 4, 5, 6, 7, and then the probability of each one, and then do your 1 variable stats with a frequency list. I'm not going to go through that process, but if you can't remember how to do that, you have questions on it, let me know. But we could just intuitively kind of go through this. We want to think, okay, 4 is right here, which means I need to have kind of equal probability on either side of it if the mean is exactly 4. So I'm not going to worry about this necessarily, but above 4, there's a 0.3 probability of getting above 4. Below it, there is a 0.6 probability, which tells me just intuitively that my mean is going to be less than 4, because I'm more likely, the average value is more likely to be less than 4. Okay, if it had been 0.5 and 0.5, or basically equal, then I could say, yeah, it's probably going to be 4. So now finding this, it's not going to be equal to 4. Is it going to be greater than or less than 4? Well, it seems to be it's going to be less than 4. So E is the answer. Okay, so there's that one. All right. Past records indicate that 15% of the flights for a certain airline are delayed. Suppose flights are randomly delayed one at a time from all flights. Suppose flights are randomly selected one at a time from all flights. Assume each selection is independent of another. Which of the following is closest to the probability that it will take 5 selections to find one flight that is delayed? So we got like a list of flights, and it might have been delayed, it might not have been. We're going to select from a random list of flights. So the reason for this is that now it's all independent, okay? And now 15%. So what is the closest to the probability that it will take 5 selections to find one that is delayed? Well, we can approach this in a few different ways. So I think we can think of this as binomial or geometric. Or we're seeing that it's going to take 5 selections to find one that is delayed. So that means the way I'm reading this is that it's going to be the 5th. So I'm going to get not delayed. So I'll put a minus here. Not delayed, not delayed, not delayed, not delayed. On the 5th one, it is delayed. That is the outcome that I want. So this is a geometric distribution, a geometric probability that on the fifth selection, on the fifth selection, I will find the delayed flight. So I know that my probability of a delayed flight is 0.15. And I'm looking for my X value here is the fifth. Now this is a geometric PDF, which is going to be just the probability and your X. And then we can just plug that into the calculator and get an answer. But remember, what we're essentially doing is we're doing the formula for this is basically, if I can think through it real quick, it's going to be the probability of failure is 1 minus P. This is a probability of failure raised to the power of X, or X minus 1, and then times the probability of success. So that's really your PDF. I might not have quoted exactly, but that's essentially what we're doing, because we're going to do now, we have a 0.85 probability that any one of these is not going to be delayed. So now I can do 0.85, not to the fifth power, but to the fourth power. And then the probability of success is going to be 0.15 that last time. So you could do your calculation that way if you wanted to, because this is more, we're not thinking of it as a geometric, but we could really just think of it as a straightforward probability problem. I want not delayed and not delayed and not delayed. So I could just keep doing this kind of calculation and just kind of go through it that way, wherever your mind takes you. But geometric PDF will get the job done as well. So if I do geometric PDF, I haven't done this ahead of time, so I'll just real quick, 0.15 and fifth. It looks like I got 0.078, and that means A is my answer. Okay, good times. Let's jump ahead. Again, any of these that we go through, you still have questions on, you can ask for more help. Approximately 9% of the residents of a large city have seen a certain theater production that is currently playing in the city. A marketing researcher will randomly select residents until one is found who has seen the production. What is the expected number of residents the researcher will need to ask to find someone who has seen the production? This is a very straightforward problem once you know what we're trying to do. It's looking for the geometric mean, okay? Remember, geometric distribution says how long is it going to take until we find the first? And we can find the probability that the first person is the fifth, the 100th person, all those different probabilities. But we want to find what's the average number of people we're going to have to ask until we see someone who sees the production. So that's going to be the mean of this distribution. So the mean of this particular random variable X is going to be 1 over the probability. And that's what our formula is for the geometric mean. And 1 over the probability of 0.09. We just have our calculator do that. That is literally all we have to do for this problem. Okay, so now let me do 1 divided by 0.09. And that is 11.1 repeating. So right here, E is the answer. So I feel like this is something that maybe some of you need to spend more time with, the geometric stuff, but that it's definitely been a source of confusion. Okay, at a certain restaurant, 35% of customers order the daily special each day. Assume that each day the customers arrive randomly and order independently. Let the random variable X represent the number of orders placed until the first special is ordered. The distribution of X is geometric, has an expected value of approximately 2.86, which is the best interpretation of the expected value. Okay, so the expected value is 2.86. So we don't actually have to do any calculations here. So each day, 3 customers will order the daily special. No, and this calculation has nothing to do with it. This represents the number of orders placed until the first daily special is ordered. So no, we're not going to get 3 daily special orders. Over many days, the average number of customers ordering the daily special is approximately 2.86. I like that one. That one seems good because remember your geometric mean, it says if we do this over and over and over again, it's going to average out to 2.86. Over many days, it takes about 2.86 orders on average to be placed until the first daily special is ordered. I like that one better, and I didn't read the second one very carefully. But yeah, this has nothing to do with the number ordering the daily special, so I should have read that more carefully. But luckily, I read the second one, or the third one, and caught my mistake. It takes 2.86 orders on average to be placed until the first daily special is ordered. For a random sample of the days, the average number of orders of the daily special will be 2.86. Again, it doesn't have to do with that. It has to, how many times until one person orders it. Each day, the ratio of the number of orders to the daily special to the number of orders of other menu items is 2.86 to 1. That is just a wild interpretation. That is not true at all. So there it is. The answer is definitely C. Okay, remember, just to make sure the concept that we're taking away here is BIFs when it's geometric, and that key right here is the first. Anytime it's asking about the first, the geometric is always related to that. In this case, the first daily special. Okay, so let's look at, I think we only have 2 more, but we'll see. An advertisement firm reports that the proportion of customers who respond favorably to a certain advertisement is 0.7. 3 simulations, A, B, and C, were designed to create a sampling distribution of a sample proportion from a population with a proportion 0.7. Each simulation consists of 2,500 trials. For each trial of a simulation, a sample size of n was selected at random, and the sample proportion was recorded. The value of n varied among the simulations. The following histograms summarize the result of the simulation. Which of the following lists of the simulation in order from the least? Which of the following lists the simulation in order from the least sample size n to the greatest sample size n? Okay, there is a lot of verbiage going on in this question, and so it's really easy to see maybe where there's some confusion. So first of all, a sampling distribution was created. So it's good to talk about this concept real quick. Sampling distribution is the distribution that would be created if we created all possible samples from the given population. And that would be modeled with a normal model, okay? Now each dot that makes that up represents a sample of size n, okay? So we don't know exactly which make that up, but each dot that makes up this model, and it's hypothetical dot making up this hypothetical model, represents a sample. Our sample is going to mesh with one of those dots. It's going to be the same. So our dot will live somewhere in this diagram, in this model. Okay, now we are going to try and figure out, basically this question is all about the sampling, the sample size. So this is sampling with proportions, and the standard deviation for a sampling distribution of proportions. So actually I should not do it that way. That would be mean right there. So it should be proportions that is going to be the square root of p times 1 minus p all over n. Now, we don't know, I mean, yeah, we do know the proportion here. It's going to be 0.7, and so the probability of failure is going to be 0.3. But honestly, that doesn't matter. We don't care what the proportion is here. It happens to be 0.7. Because remember that as the sample size goes up, the standard deviation goes down. Okay, so I will just figure out where the standard deviation is for each one of these. So here's my standard deviation right here. Okay, that didn't work out very well. It's about like that. So, you know, this is maybe about I'll just say 0.05 for right now. If I need to be more specific later, we can do that. This is going to be about 0.01. And this is right here is going to be 0.10. Again, notice that what I'm saying here for the standard deviation, it goes from the inflection point, which is about right here, to the mean, which is right there. So that's why I'm kind of looking at that gap. And that distance is what I'm measuring for each one of these distributions, which is really not different, except in the numbers at the bottom. So remember, as my sample size goes up, my standard deviation goes down. So my biggest N, I'll just put, I don't know I'll just put this as the biggest. So I'll just put 2 greater signs right here. No, I'll just put 1. I'm just trying to figure out how to show this very clearly. So greater than, so this is bigger N. This is the medium one, I'll just put N right here, and this is the smaller one, so I'll put less than N. It's not exactly the best way of showing that, I just didn't want to write it all out. So we're going from the least sample size to the greatest. The least is right here for A. C is the middle, B is the biggest, so it's gonna go A, C, B. Looks like that is right here. All right, a few concepts coming into play here, but really it comes down to this idea that as your sample size goes up, your standard deviation goes down. Okay, hopefully that was clear enough at the end. Sorry if I was confusing along the way. Okay, let me see real quick. Okay, there's 2 more problems. And these, I think, both deal with the point estimator. And this is something that we did talk about, but not to a great degree. So let's kind of go through. Samples A and B were selected from the same population. The mean of sample A is equal to the mean of the population. Which of the following statements must be true? The mean of sample A is a point estimator for the mean of the population. The mean of sample B is a point estimator of the mean for the mean of the population. And the mean of sample A is equal to the mean of sample B. Well, let's first of all talk about what we know isn't true. That if we took 2 samples, it's highly unlikely we're going to get exactly the same mean. Okay, because we're going to get different people in our sample, or whatever is this population is of. We're going to get different individuals making up that sample. So these will not be the same. So anything that says that 3 must be true, I'm going to cross out. So it's either 1 and 2 or 1 or 2 individually. So both of these are point estimators. Remember, anytime that we take a sample and we get a mean of that sample, we are estimating the population, and that is a point estimate of it because it is a specific point. The actual X bar that we calculate is estimating the population mean. Now, it just so happens that the mean of sample A was the same as the population, but that's going to happen sometimes, and sometimes it's not. And generally, we're not going to assume that it's exactly right. But they're both point estimators, so the answer here is D. Both of those are true. Okay, and just the last thing here about point estimators. We've got two distributions going on right now. These are sampling distributions for 2 different point estimators, X and Y. Okay, so this is a question about if they are biased or not. And remember, a biased estimator is one that means that the mean of our sampling distribution is not equal to the true population parameter. In both of these, the population parameter is given right here in the middle. We know that it lines up right in the middle. So the question is, if these are biased, the basic concept, if these are biased, then our mean of our sampling distribution, all these different columns right here, the mean of that is not going to equal the population parameter if it's biased. We're looking for unbiased means, unbiased estimators. So if I look at this, the distribution on the left and the right are symmetric, which means the mean is going to fall right in the middle. So the mean in this case is exactly the same. So X bar right here is going to equal this mean right here. Now, if I look on this one, I look at the left and I look at the right, those are mirror images. Those are symmetric also, which means this is going to be my X bar. And that X bar happens to be the same as the population parameter. So both of these are unbiased. And that's really the answer here. Both X and Y are unbiased. Okay, so that is really the takeaway for this problem. And that's kind of again, these problems were picked out because they were ones that were confusing for people, that were the most frequently missed on the progress checks. So I encourage you guys, if you still have questions on any of this, to kind of ask more questions about it. But that's all for today, and we will move on with semester 2.